Swayam Prabha. Digital India. Educated India.
Welcome to 22nd lecture in mechanics of materials. The last lecture we saw two different possibilities by which the shear stress distribution can be in an I section. Basically we saw that there can be a possibility of sigma xz shear stress arising when the flanges of the I section is thin, and there will be only sigma xy shear stresses when the flange thickness is thick compared to the web thickness. Okay. Flange width is small compared to the web thickness. Okay. So, basically we saw that in both the cases the shear stress values will be different depending upon how the stress are distributed. Okay. So, basically also we saw that depending upon how the section is built up, whether the sigma xz shear is going to be resisted by the nails or weld, or sigma xy stress is going to be resisted by nails or the weld, you have to use the appropriate shear stress distribution to compute the connection details. Okay, the connection shear stresses, and then do the connection detailing. Okay. So, in the last class also we alluded to the possibility of there arising a torsional moment because of this shear stress distribution. Now, I section there won't be a torsional moment because the moments are balanced, because the flanges are of equal width in both the directions. Okay. So, now we will go ahead and understand what you mean by a shear center. Okay, and how do you compute the shear center for a cross section? Shear center is a geometric property, and we will see how to compute the shear center. First, let us define what a shear center is. Shear center is a point such that when the externally applied load acts on this point, there would be no net torsional moment in the cross section. Okay. For example, if you take I section, which is of equal length on either side of the web. So, this is BF. Okay. Then what happens is your CG is at the center, this is Z, and your CG is this your CG. Okay. And the shear center will coincide with the CG because as you saw in the last class, the shear stress distribution were to be horizontal, there will not be net torsion produced in the cross section because this moment is balanced by these two are of same magnitude Q1, and this is of also magnitude Q1. So, the red Q1 produces a clockwise moment, whereas the green Q1 produces a anti-clockwise moment which balances each other, and then there is no net torsion, and your shear stress, there is a Vy acting like that, vertical shear force. Okay, to balance that there will be a shear force externally applied in this cross section at the CG, so will also act through the CG of the cross section. So, there will not be any torsion produced in the cross section if the load were to act along the CG of the cross section. Okay. So, this happens for all symmetric sections loaded about the plane of symmetry. Okay. So, basically now shear center would be a CG if loading is about a symmetric axis. We haven't defined what a symmetric axis is yet in this course, we will do that shortly. Okay. But if the loading is about a symmetric axis, that is equal area is distributed on either side of that axis, then the shear center will coincide with the CG of the cross section along that direction, okay, along the symmetry axis direction. Okay. So, in other sections the shear center will not be the CG of the cross section. For example, if I look at a channel section, we will see today by detailed derivation that for this the shear center lies here, this is the shear center, whereas the CG of the cross section would be here, this is the CG of the cross section, right. Okay. Because this is not the y axis here is not a symmetric axis, whereas z axis is a symmetric axis. So, the shear center lies on the symmetric axis z axis, whereas y is not a symmetric axis. So, basically your loading has to be along the shear center here. Okay. Now, same thing we have to see what is the shear center for an angle section and for a T section. Okay.